Hello everyone, let us start lecture 24. In lecture 23 we talked about the information what we get out of phase diagram and associated free energy composition diagram. Now in this we will try to see what other information phase diagram will not be able to give us and what are the things we need to consider to know the other aspects like morphology of the phases, or if we change the cooling rate. For example, till now we have been talking about equilibrium, but actual operation does not happen all the time in equilibrium, and whenever we have an equilibrium process, that means we have to give enough time at a particular temperature, sufficient time to reach equilibrium. Now for example, if we try to see heat treatment of steel, and in case of heat treatment of steel we follow annealing, we follow normalizing, we follow tempering, we follow tempering, martensite formation, that means hardening. So those cases we do get different morphology. Even some cases we do get some phases which are not mentioned in phase diagram, because those phases are appearing because of some martensite equilibrium condition, because of some metastable equilibrium condition. Now since we are talking about steel, so let us discuss the steel phase diagram. We know that how iron carbon looks like. So if we see the iron carbon diagram, this is my iron carbon diagram where this is liquid plus delta, this is delta, this is delta plus gamma, this is gamma, gamma plus liquid, liquid plus Cm, Cm means cementite, Fe3C. This is gamma plus, this is alpha plus Cm, this is alpha plus gamma, this zone is alpha. This is percentage of carbon, and here it is Fe3C, which is nothing but 6.67% carbon weight percent. So whatever we are considering in terms of weight percent, this is 0% carbon. Now we need to only look at the steel part. So the composition and temperature of steel part we are drawing again. So if I see this temperature 1147 degrees Celsius, and this composition is 4.3% carbon, this is 0.8% carbon. If I try to see this composition which is around 2%, this is 0.02% carbon, and this temperature in 727 degrees Celsius, this is 910 degrees Celsius. These are some important information of the steel part. So let us draw the steel part only. So steel part 2%, this is my steel part. This temperature, this is gamma, this is alpha plus Cm, this is alpha plus gamma, this is gamma plus Cm, and this particular zone is nothing but alpha. Now, here also similar to eutectic system, if we just replace those liquid lines with solid gamma line, and then we also consider alpha beta instead of alpha beta, if we consider alpha and cementite, we would come across, we will get to this particular phase diagram, which is called Eutectoid phase diagram. Since here one invariant reaction that is taking place, where gamma with a composition 0.8% converts to alpha of composition 0.025% plus Fe3C of composition 6.67%. So, this is my Eutectoid reaction. Eutectoid reaction, and this temperature of eutectoid is 727 degrees Celsius. Now, similar to eutectic system, if I try to have a composition this or this, so this is let us say x1, this is x2, and if I start from at this point and at this point, so that point, this point and this point, it will be entirely gamma, and as we go down, at some point of time it will touch the phase boundary line. For example, in this case it will touch here, in this case it will touch here. So, if it touches here, then we would get the phase that would appear first is the cementite phase, and if it touches there, so then first phase that would appear in gamma is nothing but alpha phase. Now, if I try to, and also as per this nomenclature, if we take any composition just at eutectoid composition, we call it eutectoid steel, and if we take a composition less than eutectoid compositions, that means this particular x1 composition, we call it hypoeutectoid, steel, and the composition which is on the right side of eutectoid composition, which is 0.8%, we call it hypereutectoid. So, this composition is called steel. Now, if I try to see the free energy composition diagram, it will be exactly similar to liquid solid phase formation. So, if I try to see free energy diagram, let us say if I see the free energy diagram for two situations, one case it is the alpha phase that is coming out, this is alpha, G2 alpha, and then gamma is here, this is gamma, G2 gamma. Now, the equilibrium phases, if I take a temperature, let us say this temperature T we consider. So, then our conditions are like this. So, this is gamma x, gamma in equilibrium with alpha, this is x alpha in equilibrium with gamma, and the composition what we have taken is this one, x1. So, then I would definitely get alpha and gamma, and the first step, that means the nucleation. In order to find the nucleation driving force, I have to draw a common a tangent at this point where the composition is meeting gamma line, and then this would be my delta G n, and I would get alpha phase and gradually if I hold it there at this temperature, gradually liquid would convert into alpha and the alpha grains will form. As we go down, finally I would reach to this point, and there the remaining gamma would convert into alpha and cementite, and that particular mixture we call it perlite. And whereas on the right side, if I consider this particular situation, this would be my gamma G2, and cementite if I consider this, because cementite cannot change the composition much. So, that is what the free energy curve, the G2 of cementite is much steeper, much constricted. So, if I try to see the equilibrium things, this is gamma x gamma in equilibrium with cementite, and this is x cementite in equilibrium with gamma, and x is nothing but the composition of percentage of carbon. So, there if I take this composition which is x2, then as per our concept, so we will draw a tangent at this point and then try to see this particular difference from this tangent to the free energy line of Cm. So, this is delta G n, that is the nucleation driving force, and of course, this becomes my overall driving force, and here also this becomes my overall driving force. Now, once it comes to equilibrium point, which is equilibrium Eutectoid temperature, that time situation, the free energy composition situation becomes like this. So, this is my gamma G2 gamma, and this would be my alpha, and this becomes G2 Cm, this is G2 alpha. So, we can draw a common tangent and I form, this is x alpha in equilibrium with Cm, this is x Cm in equilibrium with alpha, but I am just putting another thing which is Eutectoid, and here it is Eutectoid, and this composition is nothing but the composition of, even if there is a small amount of gamma there, so they will try to form alpha and cementite phase, and once I drop just below the Eutectoid temperature, all the gamma will convert into alpha and cementite, and that time this particular phase morphology is like this, the alternate lamella of alpha and cementite. So, this is cementite and this region is alpha, because if I try to see the mass fraction from the area measurement, then I would see that alpha content is higher than the cementite content. How come? Because if I try to see this particular phase diagram, let us say I draw a tie line here, then I see that if I take a composition this one, then this entire volume mass fraction of alpha of this composition would form, and this mass fraction of cementite of this composition would form. So, that means okay, so we have taken this particular composition. If we take this particular composition, of that particular gamma. Then when I drop it, and finally at this point I would get some pro-eutectoid ferrite or alpha, and the remaining gamma will convert into pearlite, which is alpha and cementite. So, this remaining thing would have, remaining gamma would have the compositions this. So, if I try to see the fraction of gamma and fraction of gamma, for example, if I redraw it again, if I redraw it again, this phase diagram part, this is 0.8. So, if I see this particular composition, then once I reach to this composition, that means the gamma, remaining gamma, and this would be my alpha phase of this composition, and this would be my remaining gamma. See, this gamma would have a composition this 0.8. Now, cementite is far off on the right side. So, here is the cementite. Here is the Fe3C, 6.67%. So, now if I try to find out what will be the alpha in pearlite, then that would be decided by 0.8, 6.67 divided by 6.67 minus 0.025. This is the whole mass fraction of alpha, and cementite mass fraction would be. Now, we know that these phases are appearing, but if we try to see their microstructures evolution, for example, if I go by this phase diagram, then, and if this composition is, let us say, 0.3% carbon, then at the point, if I try to draw different points, let us say this is one point, this is another point, and this is another point. So, I would have something like that. For example, initially when the point I am here, it is entirely austenite or gamma. So, this is gamma polycrystal, and if I indicate those points, this is, let us say, P, Q, R. This is gamma at P position. Now, when it goes to, as it goes down, at this point first alpha phase would appear, and those will appear along the grain boundary. Rather, it will form, first it will form along the grain corners or triple point junction. So, here the first nuclei of alpha would appear, and then they will start growing, and in the meantime also alpha can appear on the grain boundary, grain edges, and then finally if we go to R position, then I would get polycrystal of pro-eutectoid ferrite, since till the temperature reaches to eutectoid temperature, I would always get to have pro-eutectoid ferrite, and then once that remaining gamma reaches eutectoid composition, because as we are saying that the gamma is gradually enriching with carbon, because when alpha forms, alpha rejects carbon to the parent phase, and then finally gamma phase composition reaches 0.8, and then eutectoid reaction happens like this. So, this is G and this is percentage of carbon, and then I would get pearlite phase. So, this is polycrystalline ferrite, and then at the this portion like this phase microstructure appears. So, that means from starting from gamma I would get to this microstructure, and if I try to see the what will be the pro-eutectoid ferrite content, I can easily find out. I can find out from tie line. Let us say I draw tie line here just below eutectoid temperature, then I could understand this is my pearlite region, this is my pearlite. So, I have to only find out what will be the pro-eutectoid alpha. So, this would be my pro-eutectoid alpha of this composition just below. I am just talking about just below, and the remaining gamma will convert into paralytic transformation, since the remaining gamma would have this composition, this 0.8% composition, which is the eutectoid composition. So, I will get this microstructure. Now, this microstructure can appear if I do it a very slow cooling, and one process is very slow cooling is you keep the sample in a furnace and put up the furnace, and gradually that, and do not open the door, furnace would gradually reduce its temperature and the sample would get annealed, we call it annealing. And that is also called as furnace annealing. Now, if we do a normalizing, so furnace annealing is one heat treatment practice. In steel, where we do get equilibrium structures, equilibrium phases. But if I do the heat treatment, let us say I take it to austenitizing temperature, I convert everything into austenite, then I take the sample out and leave it in the air. So, in the air, when I take the sample out in the air, and then the cooling rate would be faster. So, that time we call it normalizing. That time the structure modification would be there, the structure would become like this, the grains would be much finer, which is alpha grain. I am talking about the final microstructure what we will get. So, and also then pearlite also would form So, this pearlite would form. Now, interestingly here two changes if I do normalizing. One is it becomes finer, one, and second thing is pearlite also becomes finer. What does it mean that, what does it mean about when I say that pearlite becomes finer? Means when I talk about this pearlite, we see that these are separated by these two subsequent cementite lamellae are separated by a distance, and this distance we call it interlamellar distance. we also call it as, give a notation of this. Now, if I go for normalizing, that means a higher cooling rate, this interlamellar spacing decreases, that means it becomes finer too. So, if everything becomes finer, that means the amount of grain boundary area is also increasing. At the same time, I am also getting a finer structure, that means finer perlite. So, what would happen to the hardness of it? The hardness would definitely increase. So, here the hardness would be, which will be the softest, then I will get normalizing, little harder. But if I go for a water quenching, then I would have entirely different picture, because the phases that would appear is called as martensite, and that morphology is also entirely different. So, now from our discussion it is very clear, if we, for example, if we do quenching, that means I take it to austenitizing temperature, I do form entirely austenite, then I put it in directly, I take it out from furnace and then put it in water, or which is kept at room temperature. So, immediately the temperature will be dropped, I get a martensite structure. I get a phase which is called martensite. This is a metastable phase or non-equilibrium phase, and then microstructure is a kind of sharp needle like structure. The structure becomes like this. So, then this microstructure gives a much higher hardness. So, rather it is the hardest phase, hardest sample out of the entire sample we have produced from by either furnace annealing or normalizing or quenching. Now, interestingly, the phase diagram, let us understand now, phase diagram, would it tell us what will be the microstructure if we change the cooling rate? No, it cannot tell us what is the microstructure. Okay. Second part is, what will be the fraction of phases if we cool at a different speed? Okay. It will also not be able to tell us, because phase diagram also only deals with the equilibrium phases, but here actual practice we are not dealing with equilibrium cooling, rather it is non-equilibrium cooling. So, the phase diagram would not tell us this particular information. So, we would further elaborate this part in our next lecture. Let us stop here. Thank you.